Assalamu alaikum. Today we will discuss about how we can manually apply wind load in our structures. There are several methods mentioned in the code. Today we will discuss about the All Heights method. The code reference we will use from the BNBC 2020 part 6 and method 2. This method is adopted from ASCE 705. So the wind load application process and calculations is broadly consistent with the ASCE 7 standards. Here I have developed a calculation tool following this method. In this video, I will show you how can you use this calculation tool and assign wind load in your structure. Although I will show the process for the single street shade, but you can assign wind load in any kind of structures with any kind of height following this method. Keep in mind that this method is only for the main structural frame, not for components and claddings. There are several other methods for components and claddings. In this video, I will show you the input parameters, also the result outputs, and the process of the wind load assign in the structure. In this calculation tool, I have also included user guide, code references, and 3D simulation for better understanding. In the user guide, you will find all the description and code references for the inputs parameters provided in here, and in the code references there are the main equations and the table references. Now here in the 3D simulation, you can see that, let's start this simulation. You can see that wind is flowing from the normal to the ridge direction. See here, it is the ridge, and wind is coming from the normal perpendicular to the ridge direction. So the front face is windward wall and the opposite face is leeward, and the other two faces is side wall, and here it is the windward roof and it will be leeward roof. See, in the front face the load will be act as pressure, and for other faces, the leeward, side wall, and the roof, typically the wind will act as suction. See, the red loads is representing the suction and the blue arrows is representing the pressure. If the wind is coming from the parallel to the ridge direction, the name of the walls will be changed. This will be the front face, therefore we will call this face the windward wall, and the backward wall will be called the leeward wall, and the other faces will be called the side walls. And in this direction there is no windward or leeward roof, all the roof is same. For if there is any kind of opening in the structure, there will be generate some internal pressure in the inside of the structure. See that the green arrows represent those internal pressures, and there is two kind of internal pressures. One is the positive internal pressure, which is applying pressure in the surface of the walls and the roof, and another is the negative internal pressure, which will be act as suction from the surfaces of the walls and roofs. So to calculate the value of this pressure, there is an equation mentioned in the code. This is the main equation. So in the code reference, I have included that equation. It is external pressure and internal pressure. it is here, the P is equals to Q into GCP minus QI into GCPI. So the first part is the external pressure, the outward pressures, and the internal pressures is the second part, QI into GCPI. Combining this pressure, we'll get the total pressure. So in here, if you click in the components, difference or the equations will be revealed. See, for Q, there is an equation which is provided in here, 0.000613 kz kzt kd v square I. The term of these elements is mentioned in one by one in here, that the G is the that in here you can see that the P is the net ultimate design pressure, Q is the velocity pressure active in the surface phase, evaluated as Q is equals to QZ, and for other phases it will be called Q equals to QS. That means for the windward phase it is QZ using the height Z, and for other phases it will be QH using the height H. We'll discuss it about in later. G is the gust effect factor, Cp is the pressure coefficient. In the code, for the different surfaces like windward, leeward, windward roof, leeward roof, sidewall, there are separate tables for to get the value of Cp. And in the internal part, there is Qy, which is same as the Q equals to QH, and there is another component which is GCPI. Okay, GCPI is the, if you click in here, it is the internal pressure coefficient for enclosed building. It is 0.18. See in here it is provided as plus or minus, because we have seen in the simulation there is two types of internal pressure, positive and negative. We have to consider both. For partially enclosed it is 0.55, and for open structures, as there is no possibility to generate the internal pressure, the coefficient is 0. Okay, so for internal open structures we do not have to consider the internal part. So in here you have to provide the input parameters. In this tab I have included an user guide to help you or guide you how can for the input parameters. See in here, first of all you have to select the location. Let's say that our structure is located at Gazipur. Let's select from here. The basic wind speed for Gazipur is 66.5. The yellow colored boxes or fields you do not have to assign, and this will be automatically calculated. But if you need to change, you can also change this. And here then we have to determine the exposure category. As per the structure's location, we have to select the exposure category. Seen here, exposure A, B and C. If it is located in the surface roughness condition A and fulfill the minimum distance criteria for that surface roughness type A, you can select exposure A. If the surface roughness condition falls in C, like flat and unobstructed areas and water surfaces other than cyclone prone regions, if your structure is in this roughness condition, you have to select exposure C, and exposure B will be selected if exposure A and exposure C do not apply. So based on the surface roughness, we will select our structure as exposure A, and then you have to select the case type. The case type is actually in here. I have provided a note that as we are providing wind load based on the all height method, so we have to select case 2. Case 1 is for the actually low rise structures and components and cladding. So for the all height method and main wind force resisting system, we have to select case 2. Then topographic factor, if your structure is not in the hillside, you do not have to worry about it. You can simply select the value 1. And then the directionality KD factor, there is also a table for this. For the main resisting frame, for the main frame it is 0.85, and for other kind of structures the value may differ. So for our structure it is 0.85. Then we have to provide the building geometry, like the building height from EGL to roof, that means the full height. Now we will input the building geometry. See, for the window assignment I have an ETABS model and also a STAAD model. In our structure, there the ridge height from the EGL is 7.5 meter. Let's input in here. And the eve height is 6 meter. Let's also input in here. And the mean roof height will be automatically calculated. See, in here the roof type is double slope, and the length of the building parallel to the ridge direction, that means in here it is 24 meter, and the length of the building normal to the ridge direction, this is in here, it is 18 meter. Now we have to calculate the slope of the shade. Here the slope will be automatically calculated, but if your slope is different, you can also manually input the slope angle. See, for our structure the slope angle is 9.46 degree. Now as this slope angle is less than 10 degree, the governed height h will be eve height. Otherwise, if the slope angle is more than 10 degree, the governed height will be the mean roof height. And in here we have to select the occupancy category. Come in here. Based on the selection, the importance factor will be there. Then the gust effect factor, which is 0.85. And as our structure is enclosed, so we will select enclosed building. Next we have to provide the bay length, typical frame spacing. And the bay length is for our structure is 6 meter, and column to column spacing in the end gable, so this is the end gable, and the column to column spacing is also 6 meter. So our inputs are done. See, in here you will see the basic parameters which you have provided will be in this table. In here the design pressure will be calculated. Earlier we have in the code reference tab we have seen the equation for the pressure. In this design pressure tab, the pressure will be calculated for windward, leeward and sidewall. It is different because for different kinds of wall faces and roofs the CP value is different. So therefore the external pressure, which was Q into GCP, it is calculated in here, and also the Q into GCPI, which was the internal pressure, will be calculated in here. Now we will come to the pressure table. Using this table we will assign our wind load in the structure. So in here the pressures also including the UDL is generated for windward wall, leeward, side wall, and roof. The first table is for the wind normal to ridge direction, and the later table is for the wind parallel to the ridge direction. We'll use this table to apply the wind loads in our structure. Let me show you the process. First, let's discuss about the wind normal to ridge direction. Here you can see that for the roof there is 3 rows of wind. Let me show you why it is in here. In our user guide, if you come to the design pressure tab, you will see that there are several sketches for better understanding. See in here, when wind is coming from, if your structure is long, you can see that as per the distance is increasing, the pressure is decaying. Due to this, the code reference, the value for CP, which is a pressure coefficient, it is reduced based on the length. See in here, based on the H distance reference, the value for CP is reducing. If you come to the code reference here, the CP values for roofs, you will see that if the slope angle is less than 10 degree, and for the normal direction and for parallel direction, you can see that for with respect to the value of H, the CP values is different. See, for 0 to H, the CP value is 0.9. For H to 2H, it is 0.5, and greater than 2H, it is 0.3. So in the sketch, you can see that with respect to the value of H, the values are changing. So that calculation is provided in here. As our value of structure governed height was 6 meter, governed height was 6 meter. So from 0 to 6 meter, the from windward edge, the value will be, the value is 0.9. For 6 to 12 meter, it is 0.5, and less than 12 meter, it is 0.3. So these values are with respect to the height of the structure. Okay, and later you will see another row for the smaller uplift value. In here, this value is included to also consider the roof live load. It is, you can see that in here, that in the table there is another CP value for the roof, 0.18 for all over the roof. This value is provided because you can see that in our simulation that the wind act typically wind act on the roof as suction, but the live load is act as pressure, gravity load. Okay, so in another case, the coefficient value for CP is 0.18, so that the effect of the live load will not be neglected. So let's assign these wind loads in our structure.